So for our last background talk, we have Andy Jiang from Michigan to tell us about periods, variations, Hodge factor.
Yeah, thanks. Okay, so I guess I'll start by recalling the definition of a complex variation of Hodge structure. Wait, and now be on. For now, just a complex amount of things. We usually be on some variety, but I think for now it doesn't really matter. Okay, first of all, it's going to be a local system. So, and then going to impose some data on. Oh, right, sorry. It's a local system H with a decomposition when I turn the local system into a smooth bundle, into a C infinity bundle. Hodge decomposition. Oh no, it's called the Hodge decomposition. So the Hodge. When I tensor up to C infinity, I'll have some isomorphism with a direct sum of smooth bundles. Okay, slash C infinity bundle. But it has to have some conditions. So basically, the local system, when you tensor up to C infinity, it's going to come equipped with this flat connection that tells you what the local system was. And this flat connection, it needs to interact in some way with this decomposition. So let me call this smooth bundle E. So E has connection. This is like smooth one forms. And okay, so you can decompose it as a holomorphic and anti-holomorphic part, and it has to be compatible with this. Okay, so let me say, so let FPE defined to be EAB greater equal to P and okay, so I make these two definitions, FPE and F bar PE. So here my H is complex, so I'm not allowed to conjugate, but I just make this definition. And this one is supposed to be holomorphic, which means it's stable under del bar. So if it's stable under del bar, then it has to come from some holomorphic bundle when I tensor up to smooth functions. And this one is anti-holomorphic, which means it's del stable. I'm writing so okay. I wanted to like have the definitions here and then hide it, but that's not going to happen. Okay, and then it has to satisfy Griffith transferality. So that FP is not gonna be preserved under the entire connections. Otherwise, it would just be like a sublocal system. But like the holomorphic part of the connection should only bump it up by one. So FP goes to here. And similarly for F bar P. Just like the dual condition. So this is like the 1, 0, 1 forms. 0, 1 forms. Okay. So I think I've completed the definition of complex version Hodge structure. Any questions? Okay. So now let me make a remark. So the remark is, if I know that my local system was irreducible, then from this data, I should conclude that the ranks of the EABs, the set of A's such that the rank of EAB is non-zero should be like connected. So if H is irreducible, the set of A such that EAB is non-zero, connected. Yeah, meaning it's like 1, 2, 3. It can't be like 1, 2, 4. Okay, I guess proof. It's really just like an observation. So it just follows from this Griffith's transversality. So both of the del and del bars can only move by 1. And if something is 0, then like the things left of it cannot escape because the thing it goes into is like empty. So like here I have EAB. So this is B. So EA plus 1, B minus 1, B A minus 1, B plus 1, and so on. And I assume this one is 0. Then let's look at like what the conditions tell me. So it tells me like these things. So this thing is like holomorphic. So this is del bar stable, just always. And this guy over here is del stable because it's anti-holomorphic. And then you look at like what Griffith transversality tells you, and it says like this thing can the most go here, but this is like 0. So like this part also is del stable. So E just decomposes as like E1 plus E2 as vector bundles with flat connection. Oh, I guess I should have said that the connection is flat, like this thing, because it comes from a local system. Some integrable connection, I guess. Okay, let's say integrable connection. So it decomposes this direct sum of local systems because some equivalence between local systems. Okay, any questions?
Sort by E1 and UH.
Oh, yeah, sorry, I didn't actually say what they were. Yeah, sorry. I just called these two E1 and E2. Thanks. Yeah. So I'm pretty new to all this stuff, so please ask questions. Also, please tell me if I did something wrong. I don't want to just like have the wrong thing here. Okay, yeah, so that's first part. Now let's say what it means for a complex variation of Hodge structures to carry polarization. Okay, so I guess. Oh. Sorry?
You can move all.
Yeah. So let's see how well this works. I have a feeling it's not gonna work at some point, but we'll just do this. Okay, so polarization on a complex version of Hodge structures. So recall this is like the data of some local system H, and then some like decomposition of smooth bundles. It's gonna be a map of complex variation Hodge structures from, oh, I should say what a real variation Hodge structures is just, okay, so I think for any complex variation of Hodge structures, like the data, sorry, I'm not gonna move it back, just this data. I think if you conjugate it, you get another one. and then a real variational Hodge structure is one which is isomorphic to its conjugate. So you can just like conjugate the smooth bundle, and then FP and FP bar are like gonna be like switched. Is that right? Okay. Okay. So it's the data of a map from H tends to H bar to C minus N. So this guy is weight 2n and has something in like NN component. It's roughly C. Like, okay, it's a variation Hodge structure which is just like isomorphic to C as a local system and has something in the NN component of the Hodge decomposition. And I guess typically it's supposed to like be 2 pi I to the N C something. So let me ignore this for a second. Right. So there's going to be a condition on like definiteness, but let me just talk about what this thing says. So at any point, for example, it will give a Hermitian form on H, but the form is not like a metric, I guess in general. So this is the data of the Hermitian form. Which I guess like at a point it means like lambda A B, lambda B, A lambda B, A lambda bar A B. Oh, it's non-degenerate, sorry. So it should induce a perfect pairing. Inducing a perfect pairing. Yeah, what's it saying? Okay, right. But it doesn't have this like positivity condition that you usually require, like Hermitian vector spaces, like in like when you learn in the algebra, you say like Hermitian form on AA has to be like positive if A is not zero. And here I'm not requiring this. But in fact, what will happen is that when you change this psi on the Hodge components, like you sort of alternating summits, you'll get something which is a Hermitian metric. So it's a Hermitian form such that. Okay, so I think you can. So you can use this data to produce. I guess you can use it to produce like a map of smooth vector bundles, and that one, I guess I tensor up to C infinity. That one I can restrict to E PQ, and then I like alternating sum this. So I time by I to the P minus Q, or minus 1 to the P. I'm not entirely sure, but let's do I to the P minus Q, and then I like. Basically, I alternating sum this on the different components, and this thing is supposed to be a Hermitian metric on E on the smooth vector bundle. Is this okay? Okay, so that's polarization. And I guess we're talking about it between the EPQs. So I thought it would be encoded here by the perfect pairing. I'm not sure.
Oh, you're right. Sorry.
Yeah, sorry. I should have said this. Yeah, actually. You're right. This thing, like inducing a perfect pairing, encodes a lot of information. Sorry, I should have said this. Thank you. I was gonna say this. So it encodes that EPQ using phi is orthogonal to EP prime Q prime if P is not Q. Sorry, if P is not P prime, and on the EPQs it's non-degenerate, but like depending on the parity of P, it's gonna be either like positive definite or like negative definite. which is why I have this thing. Okay, up to a multiplication by I don't really understand. Yeah, something like this. Okay. Any questions?
Even there, technology would be able to go to the fact that psi was a map of C-VHS rather than just another photo.
Right, yeah. Yeah, so this part is a consequence, and so definite sorry, my board work is kind of bad. Definite on EPQ, this part is a consequence of this thing being a perfect pairing. But, okay. This part is sort of like, from here to here is the definition. This is like an explanation. And, okay, so I'll cheat and say like, a polarization on the R VHS is this polarization on C-VHS, which is like invariant under this conjugation thing. So you can descend to a R VHS with a pairing from H tensor H to R minus N if I had a polarization on the R VHS. But let me not go into details about like changing this field of scalars. Okay, what's next? Okay, so now I want to state a theorem about polarized complex variation of Hodge structures on a quasi-projective variety. Okay, so I'm going to erase this part. Oh, I should remark something like, why does this come up in geometry? So I think Sasha told me that this comes in geometry coming from the Hart-Leschetz theorem, that you multiply the two things together and then you multiply by your Kähler form enough times so you get to the top degree, and then that induces this pairing. Yeah, maybe that one will give you the bilinear one, not the Hermitian one, so there's some like little change you have to do, but let me not go into the details. Okay, so theorem of fixed part. Okay, so let S be quasi-projective. So in fact, it'll also work for a compact complex analytic space, removing some closed complex analytic subspace. So it's like slightly more general than this, but let me just write it in this case. And I have a polarized complex variation Hodge structure in it. So this is the local system, this is the smooth bundles, this is the polarization. So this thing is a polarized C-VHS on S. And now suppose I have a section, a global section on S of this local system H. So suppose I have S, which is inside H of the entire space. So this is like a global flat section of E. Yeah, so like flat sections of E are the same as this local system. Suppose I have this thing, then I can use this Hodge decomposition to write S as the sum of things in EPQ, because it's direct sum. And all of those guys, all of the components in EPQ, they're also supposed to be flat. Yeah, so. Yeah, then as I write as sum SPQ, just each one of these things is EPQ. All of those things are also flat. Yeah, so okay, so maybe let me remark that this is not true if S is like, I don't know, like an open ball. It's only sort of like a global statement. Yeah, I'll leave the exercise for you to see. Okay. Oh yeah, okay. So this is the statement, theorem of fixed part, and I'm not gonna give the proof. Yeah, so the proof is sort of like you reason by like the smallest SPQ to you show that thing is flat, and then you proceed by induction, and then there is some like analysis argument using like Fleury subharmonic functions, but I can't do it, so I'm not gonna do it. Yeah, so this is the statement. But I'm gonna use it to show that if you have a irreducible complex variation of Hodge structures, then it emits at most one polarized. If I have a irreducible local system, it can be at most. It can be enriched into a polarized C-VHS in at most one way, up to like changing the weight and like the grading and things like up to like dumb things. There's only one way, at most one way. So probably on a plus projective S, any reducible C local system, the light, C local system H can be an enhanced into, sorry, I'm gonna grab a longer piece of chalk. Polarized C-VHS in at most one way up to like up to the ways that you can change it that you can think of. Like weight shift, grade shift. I guess you can technically dilate this phi. Is that right?
Maybe one way to say it is tensoring with a C-VHS on the trivial ring model.
Yeah, thank you. Up to tensoring with a C-VHS on trivial local system C. Okay, yeah, so how can we show this? So the way is that suppose I have two polarized C-VHS on the same underlying irreducible local system, then for any two variation of the Hodge structures, there is actually a variation of the Hodge structures on the smooth bundle, which is like Hom from one into the other. It's just like the data of the variation of Hodge structures, you can just show it has sort of like an internal Hom. And we're going to produce a section of that, a flat section of that, that variation of Hodge structures, just because the two have the same local system, so like there's going to be some isomorphism, which is flat, and then we use it to produce something which is in a pure Hodge component, and then it'll be like a morphism of variation of Hodge structures. Okay, I'll write it. But it's sort of, we just have to apply this. Okay, so, and we have to use the fact that there's sort of internal Homs. So, proof. Yeah, so I can consider the local system which is like the dual of H tensor H, or internal Hom from H to H in like local systems. So this total I'm gonna use to write internal Hom. This thing is gonna be part of a package of a polarized complex variation Hodge structures. Like this entire thing has internal Homs. So yes, here I have the internal Hom of the vector bundles. Sorry, not smooth bundles. I should give names. Okay, sorry, let me think about how to write this. Suppose there's two ways. Okay, suppose E, which is H tensor to Z infinity, is direct sum of EPQ and also equal to direct sum of E prime PQ. Like I have two Hodge decompositions on this same locus system. Then I can use the two things to produce an internal Hom version of Hodge structures. So like the let me write first. Okay, sorry. So basically, like, there's an internal Hom. So if you Hom the two vector bundles, there will also be a grading on the Hom, and then you use that grading to produce some. Okay, I think you guys know what I mean. Some version of Hodge structure. And then here you also have a polarization phi. Okay, so let's say this one's polarized by phi, this one's polarized by phi prime. Phi dual tensor phi prime. But now we observe that this polarized C-VHS has like an obvious flat section, just like the identity section here. Okay, so this is a polarized. This is not the statement. Okay, there's a C-VHS. Obvious section, obvious flat section, sorry, non-zero I guess. And then we're going to use the fixed part theorem to make this flat section into a sum of like pure Hodge weight flat sections. So, okay. Oh, I erased the thing. Okay, whatever. So the obvious section is like identity. So like identity is like inside this local system. So we can write it as some sum of like the components of identity inside Hom like okay, E some E prime Q cube. And one of these things is gonna be like non-zero. All of these things are flat, sorry. All of these things are flat by the theorem I'm gonna use. And one of the things is gonna be non-zero, and then that thing we use to just create a map from the two variation of Hodge structures. So choose non-zero component. And what does it mean that this thing is a flat section of this Hom? So it's going to mean that there is some polarized, Daniel says some polarized C-VHS on the constant local system that maps into my okay, let's say Hom H1, H2. Now I'm thinking of the H's as polarized variation of Hodge structures with the two structures. And that will produce some map from C tensor H1 into H2, but because they're like irreducible, this map has to be isomorphic. That was way longer. I just said the same thing so many times.
Maybe you were saying, so only one of those Q's can be non-zero.
Only one of those.
Otherwise, the space of columns, those 5 columns would be more than one-dimensional.
Because the total space is. Thank you.
There's no choice.
Okay, thank you. So gives C tensor H1 goes to H2, but by non-zero map, but it's isomorphism by reducible because our local system is irreducible. Okay. Yeah. So, any questions about this? Yes.
How do you know that the identity map on the local systems will also give you it in both, like?
Well, it's just some flat section of the smooth bundle. There's no identity because on the smooth bundle side, because the two bundles are not the same as smooth bundles. Well, sorry. As when I write the decomposition, the two bundles are not the same as direct sums, but then there will be some flat section on there. Yeah, like on the local system side, it's just like Om, so there's an identity. And then on the smooth bundle side, it will produce something here which is flat. That's the thing. Yeah. Any other questions? Sorry, what do I do next? Sorry, a second. Okay, period domains right here. Okay, let's see. Let's try to move these boards over there. So we have the definition of variation of Hodge structure. Might be. Okay, it'll be helpful for me to have it here. Let's put it here. So I'm gonna erase this one. Okay, so period domains. Yeah, so period domains is like a moduli of Hodge structures. A period domain is like a moduli of Hodge structures, maybe polarized Hodge structures, on a fixed vector space with some choice of weight and Hodge numbers. So period domain is roughly the space of Hodge structures on a trivial, on a fixed complex vector space with some fixed weight and Hodge numbers, and maybe polarization depending on the period domain. Yeah, so for each one of these choices, there's some period domain. And I think it has a more precise description of what a map into a period domain gives you on your original complex manifold. And so for that, I'm gonna restrict the case of period domains for polarized complex variation of Hodge structures for purposes of this discussion. So this is like a general statement about like different types of period domains. So but now I'm gonna try to be a little bit more precise. So for H, some vector space, psi H consider H bar, C Hermitian form, which if you recall is not necessarily positive definite. What else do I need to fix? Okay, Hodge numbers, which is a dimension of the EPQs. And the weight. Okay, so fix weight. Right. Okay, so then there's some complex analytic space. So there's D complex analytic space. Such that mapping into it has some like functorial points that we can describe. Okay, I think. So such that a map from S to D is the data of a variation of Hodge structures with a trivialization of the local system, but without Griffith's transversality, which luckily is not on these two boards. Sorry. Okay. Is the data of a polarized by this particular one, polarized C-VHS with underlying local system So the trivial one on H. So I'll write H, but like this H is not actually allowed to be any interesting local system. It has to be trivial. Okay, maybe a very trivial. And also the polarization is just fixed. Sorry, with the Hodge numbers and weight. Okay, Hodge numbers. Okay, so I just said like this property, but I guess it's not clear this thing exists.
For S, you just take complex vector.
Yeah, just take complex vector. That's okay. I think it's yeah. Okay. Okay. So. Yeah, so let's roughly sketch why this space exists. So I think the idea roughly is that once I fix this psi, we had this condition, right, that the EPQs are orthogonal to each other. Right, so the EPQs being orthogonal to each other says that the FPs and the F bar and minus P's are sort of orthogonal complements, because from definitions. And so actually the data of the F bars is not important once I have this local system with a polarization. So the data is sort of like completely determined by the data of the flag FP. Okay, yeah, it's completely determined by the flag, and actually I think like generically any flag should give rise to one. I think I wasn't sure, but I think this is right. But generically every flag, every filtration on with these Hodge numbers, every filtration of your holomorphic vector bundle, which comes from your trivial local system H, will give rise to one of these polarized C-VHSs, because like there is some choices in which you break the permissionness of the vector bundle, but that like choice is like a small condition. It's like some close. So it'll just be like open inside a flag run. So, guess should write one psi data f bar. So, I guess I want to say first of all the data of the EPQs is determined by the data of the FPs and the FP bars. So, the data of the EPQs determined by the two filtrations FPE and F bar PE by holomorphic and anti-holomorphic bundles. But also from the same polarization, the data of the anti-holomorphic is like irrelevant. And the condition that it's like a polarized C-VHS is just satisfied generically. For generic flag of the right ranks, correct ranks, which depends on the Hodge numbers. You'll get a polarized Hodge structure. On H. Which means like D is open inside this flag variety.
Can I raise one objection?
Yeah.
So I guess like this D is topologically open in this flag variety, so it's like not a zero skew. So somehow
Right.
it's generic.
Sorry. Yeah, this is wrong. Yeah, it's for open conditions. Thank you. Okay. Right. Generically, it's not true. It's like some cone. Sorry. Okay. Okay. What do I say? For a open subset of flag. Open subset. Thank you. Of flags of correct rank. This is true. Yeah. So like the condition you need to impose is a determination metric and it's like some cone condition. So this is open instead of this thing, which by definition is the flag variety. Okay, and that gives it the complex structure. And so we get this construction roughly. Any questions? Yeah. Okay, let me say what happens to the period domain for a polarized real variation of Hodge structures. So, as far as I understand, if I have a real vector space with a bilinear form, it should induce one of these complex ones, which is invariant under conjugation. So that means I think for the complex period domain that corresponds to it, there is going to be some automorphism whose fixed points is like the real period domain, but like this automorphism is actually complex analytic coming from like this universal property, and I think it'll construct also some complex analytic space with the correct universal properties. And so there, I think there's sort of like, to go from the flag variety to the period domain, you need to first impose a closed condition and then an open condition. But for my complex polarized variation Hodge structures, I only impose the open condition. Okay. Okay. Guess a little bit of time. I guess I want to say a little bit about what Griffith's transversality says. Okay. Yeah. So okay, let me say in words. Period domain is open inside the flag variety, which is like GL quotient by parabolic, and also if you have a particular choice of decomposition into EPQs on your vector space H, which makes it into a polarized Hodge structure, you can use the unitary group corresponding to the Hermitian form to get to any other one, just by like choosing a correct like orthonormal basis. And then, so it'll show that the period domain is actually also some unitary group quotiented by the fixed point of this action, which is like a product of like unitary groups. Okay, Griffith's transversality. So notice that like in my condition universal property, it's like a polarized complex variation Hodge structures. Okay, I should have said this. Minus Griffith. And we want to know sort of like what the map into D should look like if it satisfies Griffith. So it's like some extra condition on a map into D for it to satisfy Griffith's transversality. And for that, I'm going to describe sort of like the tangent space of a particular point in the period domain. So suppose X is in the period domain. So we said it's sort of open inside of a flag. And so the tangent space is going to be sort of the same as what happens when you're inside this flag variety, which is basically, it's a homogeneous space. So parabolic. It's a homogeneous space under the action of GLN. So the Lie algebra of GLN maps into the tangent space, and the kernel is like sort of the Lie algebra that comes from this parabolic. So this isomorphism, I guess I choose a point. So it's open flag. Okay, so tangent space of D is like the algebra of GLN, which is, or GLH, quotiented by the Lie algebra that comes from this parabolic. And you can also write it as endomorphism of H okay, sorry. So this particular point gives, so the point gives a Hodge structure on H, polarized Hodge structure on H. So this gives on H, because that's what it means to be a point in the period domain. And so endomorphism of H will have a structure, a polarized Hodge structure, and you can also compute that this is the same as endomorphism H quotient F0 endomorphism H, where F0 comes from the Hodge structure on endomorphism H. Yeah, so inside this vector space, there is like F minus 1 endomorphism H, quotient F0 endomorphism H, and that is sort of where the tangent vectors have to go if you're satisfied Grizzly transversality. Okay, I'm not gonna like prove this in detail. It's some calculation you can do.
So we're quotienting by, that depends on x, right?
Yeah. This depends on x. Right. So this gives you
But at the math fraction.
this. Sorry. This one depends on x. Ah, okay. Thank you. Okay. Okay, I guess. A little bit apart. 7 minutes. Okay. Let me say in words. Okay, so from the data of the holomorphic connection on E, which is, so remember in the beginning we had sort of this connection, flat connection on E, it decomposes in holomorphic, anti-holomorphic part. From the holomorphic part, we can get sort of a Higgs field by restricting to the part that changes the grading of the Hodge component by 1, and that Higgs field, I think, is also equivalent to the data of the map of tangent bundles if you have a variation of Hodge structures. Okay, let me write it. Sorry, that was confusing even to myself. So recall now this, and if you restrict to EPQ, it can only go to EP minus 1 Q plus 1 EPQ, and this part that goes shift by 1 is the Higgs field. On Gur F E. And this data of the Higgs field, I think is equivalent to the data of the derivative of the mapping to the period domain. So, so for a variation polarized C-VHS, where I trivialize the local system, it corresponds to some map from S to the period domain, and the derivative of this map is sort of encoded in the Higgs field information. Okay, so I guess in 5 minutes, should I try to do this? I can try to sketch this result of Deligne on the fact that if I have a fixed dimension, the number of integral local systems that support the data of an integral polarized variation of Hodge structures is finite. And that'll be very, very sketchy. I think Daniel already mentioned this result. Sorry, I didn't write the result. So, 1 and 2. Writing integer n number of C local system think both Z and Q. That's right, both Z and Q.
So I think you want Q local system.
Okay.
Which is
I see. Thank you. Which Z polarized Z-VHS structure is finite. Yeah, okay, so roughly how it works is that I guess it makes sense. So, idea.
So here the role of n is just the weight.
Ah, sorry, thanks. It's the dimension.
Oh.
Yeah. Dimension. Sorry, thanks. Okay, so the idea is that if you fix a choice of like Hodge numbers, like enough data to get a period domain, so for fixed Hodge numbers, polarization, you can get a bound on, okay, sorry, let's say again. Okay, so I fixed something in Taiwan of your S. There's a bound on the coefficients. So if you have a local system, this object is going to produce some matrix coming from monodrine. And I guess it's up to conjugation, so you have to fix sort of a nice basis on coefficients of the action of sigma action. Sigma, which is uniform across okay, right. Uniform across the different variation of Hodge. Nice basis, which is uniform. And to do this, roughly speaking, you take the universal cover of S and then you endow it with some metric so that the mapping to the period domain always decreases distance, and that gives you sort of bound on coefficients, because sort of the coefficients is detected. So for any loop you pick, it gives you like a point in your universal cover, and because it decreases distance, there's some like bound for each period domain, how big this matrix can be. And okay, I'm gonna just say the rest in words. And the next thing you have to do is you have to show that like which period domain doesn't matter if you have a fixed dimension, and then you sort of show like the choices you can make for Hodge numbers is also like finite, so you can get a sort of global bound on these local systems of fixed dimension for a particular element of pi 1. Sorry, you have to turn the bound on the coefficients into a bound on the trace of this element. So you can get a sort of global bound on trace of the action of this element for any local system dimension n that underlies a polarized Z-VHS. And then finally, you have to show that you can pick finitely many elements of pi 1 to determine the traces of all the elements of pi 1. That's also some stuff you have to show. And then, like, because the traces of these finitely many elements have to be integers of some fixed global bound, there's only finitely many choices. And for each one of those choices, because the local systems are reducible, because the local systems are semi-simple, there is this sort of unique local system that can have those traces, like because the character of the representation recovers the representation because it's semi-simple, and then I think you're basically done. Sorry. Questions? Yeah.
Can you say again what is the condition? You said the derivative for this
Griffith's
map
transversality.
your domain to have Griffith's.
Yeah, sorry. Yeah, so here inside this thing, there is f minus 1. So it's some sub-bundle, tangent bundle. You have to like map inside the sub. Yeah, sorry.
So just to clarify, you use the irreducible local system while proving this theorem.
I use semi-simplicity of any local system.
Oh,
Yeah,
Alex.
to show it's determined by character. And then, yeah, that's part of it. Sorry, the last, I don't think I get nearly close to enough for you to understand.
Questions?
Yeah.
You have found on how the number grows in n, and could it
Sorry, I
probably be
really
related,
have no idea.
could it probably be related to controlling those coefficients?
Oh, yeah, there is some way to. Okay, maybe I should defer this question to someone else.
I think it's not really well understood. So of course the bound depends on the variety, right? For example, I think the following is open, like in range over, let's just pick Z for now, and then range over all curves of genus G. You could ask, is the bound independent of the common structure on the curve? That's not. Yeah, so my feeling is that probably it's correlated to
I guess the bounds in terms of M, that's theoretically effective.
yeah. For fixed.
Yeah.
So you say for fixed variety when n grows, you can
I'm saying there is the bound can be made effective. We just look at the first. I don't know what.
Yeah, for sure. For sure.
I'm
Very,
very
very.
Maybe I missed this, but did you also say that there was a period domain for when it's not trivial local system?
Yeah, so what happens with this non-trivial local system is that, okay, I think there's, even if you have without any very Hodge structures, like to have a modular of non-trivial local systems, there is some like stackiness of like automorphism. So I think what happens if you have a non-trivial one is that you can go to like a cover which is trivialized and then map to the period domain. So that means you can map to the period domain quotient, like the image of your pi one.
Oh, see, is that why you went to the universal?
Here, yeah, right, yeah. So here the period domain is only gonna parameterize the local system when it's trivial, so that this loop of pi one only gives you a point. It gives you a point of the period domain when I pass the universal cover for a fixed with VHS. Yeah.
Anything else? All right, let's thank Andy again. This is a quick break.